4 exciting works to hear about. And our first speaker is Robin. He'll tell us about a paper called "With a Few Square Roots, Quantum Computing is as Easy as Pi."
Thank you. So, can you hear me? Perfect. Yeah, so thank you for the introduction. I'm Robin. I wrote this paper with these lovely people. And I'm here to talk to you about a particular view on quantum computing as reversible classical computing with a few square roots. So what's that all about? Well, let me start with something completely different. So a few years ago, I read an interview with Dorita Haronoff, who is a researcher in quantum algorithms. And she said something that really stuck with me, because she said that it's really something that's special for quantum computation because it's somehow complete. Quantum computation is some kind of completion mathematically of classical computation. I think of this as maybe similar to the fact that the complex numbers are an algebraic closure of the real numbers. Now, as far as I read this, she uses the algebraic closure of the real numbers as an example of the kind of completion that she has in mind. But what I'm here to tell you about is that maybe this intuition is a lot more precise than maybe she had imagined. So what's going on here? Well, let's start by recalling a bit of algebra. So the algebraic closure of or say that a field is algebraically closed when every non-constant polynomial has a root in it. So what are examples and non-examples? Well, I guess sort of the famous non-example of this are the real numbers, right? Because if you look at a polynomial like x squared plus 1, this has no real roots, right? And this is because, well, the negative reals do not take their roots in the reals, so they take them in the complex numbers. So to actually get a solution to a polynomial like this, you need to go to the algebraic closure of this field, which turns out in this case to be the complex numbers. Now, what does this have to do at all with quantum computing? Well, let's talk a bit about that. So let me just recall, since I am the first, speaker of this session, that a unitary is a complex n-by-n matrix, which is invertible, such that its inverse is its Hermitian adjoint. Now, the reason why you care about unitaries is because they give semantics to quantum programs. A lot of people know this. What I think maybe fewer know is that they're actually also a bit like numbers in that we can form polynomials over them using just matrix multiplication and true-wise sum. And they're even quite well behaved as numbers, in the sense that if you consider a polynomial of the form, say, x squared minus v for any unitary v, this actually is going to have a unitary solution. And the reason why is, well, because every unitary has a unitary square root. So then you may wonder, okay, is the same the case sort of classically? Right, so let's look at the classical unitaries. And what are the classical unitaries? Well, they're just the permutations, right? Indeed, you can actually define a permutation of n elements to just be an n-by-n unitary with Boolean entries. So, like this, for example. Now, permutations, again, are sort of computationally interesting because they give semantics to reversible classical programs. However, since they are unitaries, right, we can consider them as numbers, but actually as numbers, they're not as well behaved as the unitaries are. Because, well, if you look at the same kind of polynomials as we had before, then it's not the case anymore that actually these have solutions in the permutations. So in other words, not every permutation has a square root in the permutations. So here's one example of one that does, right? And here's one example of one that does not. So from this, we sort of make the observation that, well, not all reversible classical programs have square roots, but all quantum programs do. Then you immediately start to wonder, well, is this a defining feature of quantum computation, the presence of square roots? Or I guess, like more operationally, can we recover, universal quantum computation from just classical computation with, certain extra square roots? And as you may have guessed from the title of this talk, the answer is yes, but stay tuned to find out. So, well, to sort of start on this journey, well, first we need a programming language for permutations, right? For the classical reversible things. And we have one of these. We have, it's called Pi. And Pi is not a very interesting language. I usually tell people that this is a very boring language. But it's cool for 3 reasons, right? So the first reason is that because it takes its semantics in Rig groupoids, and Rig groupoids are exceedingly well studied, so we know a lot about these, right? So that's very nice. The second part is that pi admits the Toffoli gate set, so it's universal for reversible classical computing. Right? So in other words, every finite permutation that you can think of actually has a denotation or is the denotation of some pi program. Right? So pi is universal for these permutations. And the third fact why this is interesting is because actually it turns out that these Rig axioms are sort of enough to reason about all of the permutations, right? In a sense that, well, two terms are equal as permutations if and only if I can prove it using just the Rig axioms. This is a very strong property. So how can we use this to talk about quantum computing? Well, we'll need a few square roots. So these are the ones. So what we'll do is that we'll start with this simple language, and then we'll extend it with two base isomorphisms. So one which we'll call W, just from 1 to 1, and one which we'll call V, from 2 to 2. And since we don't just want any random junk, we also need some equations to actually make sure that they're well behaved. So the first equation says that V is the square root of X, so the NOT gate. Okay? The second one says that W is an eighth root of unity. In this case, you can think of the identity on the unit as just the number 1. Here we're saying that it has an eighth root. Okay? And then there's the third equation. And this one, well, you could actually talk a lot about this. It's surprisingly deep. But I think the best way to think about this is, well, VSV and SVS are actually both up to the same global phase encodings of the Hadamard gate. And these are two different Euler decompositions that we're just asserting to be the same. Okay. And that's what we're trying to illustrate up here with these two trajectories on the block sphere. Now, just using these two additional isomorphisms and these three equations, we're done. That's all we need for universal quantum computing. Call the resulting language square root of pi. So what do its models look like? Well, as before, the models of pi were Rig groupoids, so the models of square root of pi are still Rig groupoids, but it'll have some more stuff, right? It'll have some distinguished maps, omega from I to I and b, from I plus I to I plus I, and of course they have to satisfy the equations that we had before. Now, we can see now that the equations are not just convenient things that we actually just make up and if this were true then that'd be very nice. Right? If we actually choose omega to be a bona fide eighth root of unity, and we choose v to be a bona fide square root of x, then we see that these are actually satisfied in the category of finite dimensional Hilbert spaces and unitaries. So this actually is something that says something about the real world. Okay, very good. Now, well, what can we do with it then? Well, since this is an extension of pi, right? We can of course represent all classical reversible gates, but we can also represent things that are distinctly quantum, like these phase gates, Ts and Z, and also the Hadamard gate that I talked about earlier. Although the Hadamard requires this notion of an abstract scalar multiplication defined in this way. And the reason why I'm very confident to say that these are the phase gates and the Hadamard gate is that when you take their denotations in unitary, then you get precisely the thing that you'd expected. And so we can use this with sequential and parallel composition from square root of pi to represent circuits in various gate sets. So for example, this circuit becomes this square root of pi term. But we also have an equational theory about these, right? Because, well, the models were just Rig groupoids with some additional axioms. So this allows us to actually not just represent circuits, but actually also reason about them. And why is that interesting? Well, recently there's been some work done, mostly out of Canada, on giving sound and complete equational theories for various quantum gate sets and unitary groups. And so this actually allows us to sort of show equational full abstraction, or these like equational soundness and completeness theorems, just by showing that these equational theories are actually implied by the axioms of models of square root of pi. So that's what we do. So this is sort of the kind of theorem that we show that two terms are equal as unitary matrices if and only if I can prove that using just the axioms of groupoids and these three axioms U1 through U3. Now, we don't show this for all terms. We show them for terms of a certain form, corresponding to representations of circuits formed using various gate sets. But really, what we did was that we looked for these equational theories. We took all of them we can find, and actually managed to show that all of them were implied by just these three equations and the axioms of groupoids. So here are the theorems that we managed to show. So we managed to show full abstraction for all Clifford circuits of arbitrary size, right? Clifford+T circuits of at most 2 qubits, unitaries with entries in this ring. So these are what we call the Gaussian dyadic rational unitaries, and also Gaussian Clifford+T circuits of arbitrary size. Now, these two are not universal, right? The first one because, well, the Clifford gate set is polynomially simulable on classical hardware. The second one because, well, it's bounded to only have at most 2 qubits, right? But the last two ones are actually universal. So we can sort of approximate any unitary using either of these two. Now, to sort of wrap up, well, what have we shown? Well, we've shown that equationally sounding complete universal unitary quantum computation is just read groupoids with 2 distinguished morphisms and 3 additional coherence conditions. What's the problem? And aside from this, well, we have a formalization in ACTA, which includes many of, not just the language itself, but actually also many of the lemmas and theorems that we've proved in the paper. So you can see Jacques' GitHub for that. Now, a central question here is, I guess, how deep does the rabbit hole go, right? So it seems here that, when we choose these, square roots very precisely, this works out. But let's say we want more accuracy, right? So this seems to be capped at, say, Clifford+T. But let's say we want not just a T gate, but say a square root of a T gate, right? Can we sort of get that and sort of still retain full abstraction? I mean, I don't see any reason why this wouldn't work. So, because the phase gates, well, I mean, there's nothing really special about, say, the T gate in this framework, right? It works just as the S gate or the Z gate or so on, right? But the primary roadblock to this is actually that even, for, say, Clifford+T beyond 2 qubits, we don't actually know of any, sound and complete equational theories. So we'll need, more work on that to actually be able to say that. Though I am, willing to conjecture at this point that actually square root of pi is going to be equationally fully abstract for all Clifford+T circuits. And I think that's all I had to say. Thank you.
Thank you, and we're ready for questions. So until someone else comes up with a question, I'll ask a question.
I have a very naive question.
Oh,
as somebody who's worked in full abstraction in classical computing,
Yeah.
Can I ask why it matters?
Why it matters in this case? Right, so, well, so here, right. So in this case, this is about, well, can you prove, well, there are sort of two things to it, right? So can you represent all of the circuits, that you need, right, in your work? And can you actually also, prove that the kind of optimizations that you want to do on them are sound, right? And universality takes care of the first, right? Can I represent sort of all of the ones that I care about? And full abstraction, or equational soundness and completeness, takes care of the second one. Can I sort of represent all of the?
But only in this little box, right? And when you add things to this box, full abstraction goes away and optimization goes away.
I don't follow this. Maybe we can.
So what I'm trying to get at is full abstraction gives you a syntactic handle at semantic ideas, right? And it's cool if a compiler writer has these things available. But in classical computing, which is something I know, I will tell you that optimizers are not really written with full abstraction ideas.
Okay.
You need contextual observation equivalence as opposed to observation equivalence, and then you have the full abstraction is just gone, right?
Okay.
We don't use it. And so I'm wondering why quantum seems to be so heavily relying on full abstraction as opposed to classical, because you're connecting the two, and the connection doesn't quite make sense. Sorry.
Right. So I don't think that I'm relying on anything in particular for quantum that I wouldn't for classical, but maybe this is a discussion that we should take afterwards.
Yeah, thanks, Robin. So you had a result that said that basically unitary is an initial model in some sense of the theory, right? But I was a little bit confused about the formulation you had there on the slide. It said like if you have any model, the next one, yeah.
This one.
No, the next one, where you had like if and only if you have any model and the unitary model. Yeah, this one. It says if and only if. Can you explain why it's an if and only if? Because it seems like any model, in any model, if the terms denote the same value, that implies that it's in unitary. In other words, it seems like unitary is the only model.
Oh, no, unitary is not the only model. And in fact, so we have a result about like a related initial model, but this isn't unitary. This is unitary with entries restricted to a certain ring. So it's actually restricted to, where you go, this Gaussian dyadic rationals, yeah, this ring. So if you take unitary, it's restricted to that, and this is actually going to be an initial model. But unitaries, as it stands, is not an initial model of this, right? Because, well, you can represent you have all sorts of junk, in unitaries that are not, the digitization of these things. So what I'm saying is that well, I'm not claiming full abstraction for all things. I'm claiming full abstraction for certain classes of terms, right?
So you said we don't have a sound and complete equational theory for Clifford+T, but we do have a sound and complete equational theory for a universal circuit model, I guess, with arbitrary ZNX rotations, the result by Clement and the group out of Candela.
So is this the love calculus PPS stuff?
I don't believe so. I can tell you the title. It's just called the complete equational theory for quantum circuits.
Right, but this is the one that they derived from this like optical quantum computing thing, right?
I didn't think that was how they got the result, but I haven't read it that recently.
So if it's the one I'm thinking about, then this isn't actually sort of a fully equational theory in the sense that they actually have, existential quantifiers. So, well, they're not really comparable in that sense.
Sorry, why aren't they comparable?
Well, so their equational theory isn't actually fully equational, right? They have existential quantifiers, and they require that you do some computation on the side, using, say, a different, not even a reasoning system. You have to compute some equations to figure out, what are the right things to plug in. There are these three numbers. I think it comes from an Euler decomposition or something like this. And it's this trick that allows them to sort of, get completeness by saying that, if you can compute the Euler, basically the Euler decomposition of arbitrary things, then you can prove the thing that you need.
I might be referring to a different paper, but we'll take it offline, I guess.
Yeah, sure. Okay.
Yeah, I'm afraid we have to take other questions offline.
Okay.
Let's thank the speaker again.